After Chapter 9 on gases, we have Chapter 10 that is on liquids and solids. And one thing that liquids and solids have that gases don't is interaction between the molecules and the atoms. So these are very close together. They're in contact with each other as opposed to gases, which are very far apart. And so the molecules can be attracted to each other differently, more strongly or more weakly. We have a list here of the types of intermolecular forces that we could have between the molecules. They're in order from weakest to strongest. All of these are based on positive and negative attractions. When we have nonpolar molecules, we mentioned that means that the molecule has even distribution of electrons. So we don't have a positive end and a negative end of the molecule. So here I've tried to draw a nonpolar molecule showing an even distribution of electrons and a polar molecule showing more of the electrons on the left side, fewer on the right side. So we have a slightly negative and a slightly positive end of the molecule. So these molecules are going to stick together more because the negative end of one molecule can stick to the positive end of the next molecule, and so they can have a little bit more of an attraction for each other. The nonpolar molecules, it's hard to have that happen, but if you have a fairly large surface area, a fairly large molecule, then the electrons might temporarily be more on one end than on the other. So it's kind of like a temporary dipole. When the electrons are traveling more towards this end, if it just so happens that they, at one instant, are more on this end than on the other, then you could have a temporary dipole. So that would be, of course, weaker than a permanent dipole in a polar molecule, but that's pretty much the best source of attraction we have for non-polar molecules. That's what makes it the weakest intermolecular force. It would be more prominent if you have a larger molecule, because then it takes longer for the electrons to go around, so they might be spending more time on one end than on another. If they have a large surface area, they are called polarizable. Then we have molecules that have a permanent dipole, like this second one that I drew. For whatever reason, more electronegative elements being on this end, we do have a permanent case of more electron density on this end than on this end. And so we have a slightly negative and a slightly positive side of the molecule. An extreme case of this is called hydrogen bonding. When a molecule has an OH or an NH or an FH group, these differences in electronegativity are so extreme that it's the same thing as being polar, but it's so strongly polar that it has a special it's a special case and it has a special name. So it's like a super dipole-dipole interaction, and that's called hydrogen bonding. I wanted to point out this chart in your textbook that is a pretty dramatic illustration of the strength of hydrogen bonding. They have a comparison of elements in group 15. So we have phosphorus, we have arsenic, we have antimony, and then above phosphorus would be nitrogen. So we have PH3, ASH3, SBH3, and then NH3. If it followed this trend, ammonia would have a boiling point here. And so the same thing would occur with the halogens, HI, HBr, HCl, should put HF around here. And then of course tellurium, H2Te, H2Se, H2S would put H2O, or water, about here. So following the trends, just given the surface area and the molecular mass, this is where you would expect these boiling points to be. In reality, however, water, hydrogen fluoride, and ammonia have much higher boiling points than these trends would indicate. And these higher boiling points are caused by this extreme polarity of the molecules known as hydrogen bonding. So these molecules are much more strongly attracted to themselves than you might expect, just given the surface area and the mass of these molecules. Your textbook also points out that the double strands of DNA, the base pairs in the middle of DNA, are held together by this hydrogen bonding phenomenon that we are talking about. So I encourage you to check out those diagrams that your textbook has to show you. Of course, if you have a full negative or positive charge in a molecule, then that would be an even stronger bond than the hydrogen bonding or the permanent dipole. Because instead of having a partial negative and a partial positive, you have a full negative charge or a full positive charge in the molecule. Ionic compounds are more difficult to compare. If you do have ions, they are going to be more strongly attracted to each other than this polarity and the hydrogen bonding, and they are not molecules. So it's a little bit hard to compare it directly, but if you do have a full positive or negative charge in a molecule, then that is going to be a stronger bond than a polar situation. For something to be polarizable means that it is larger, it has a larger surface area, and so the electrons can be pushed more toward one end than to the other, or they'll spend more time at one end than on the other. And so out of these three choices, bromine, chlorine, or iodine, iodine is the largest. It has the largest surface area, and so this would be the most polarizable. Then the next down in size would be bromine, and the smallest of these three would be chlorine, so this would be the least polarizable. This polarizability would create a stronger London dispersion force in these molecules. So all of these molecules are nonpolar because we have even electronegativity between one iodine atom and another iodine atom, or one chlorine atom and the other chlorine atom. So these are all nonpolar molecules, and that means they are depending on their London dispersion forces for that intermolecular attraction, and that in turn depends on polarizability. And so the most polarizable, the most London dispersion force would be for iodine. That would give it the highest boiling point, and then this chlorine would have the lowest boiling point. And this is pretty evident because at room temperature, iodine is actually a solid, bromine is a liquid, and chlorine is a gas. So the boiling point of chlorine is below room temperature because it's already boiled by the time you get to room temperature. It's already a gas. And so a gas and then a liquid and then a solid, it's very evident that we have the highest boiling point because this has to melt first before it can boil. This is already boiled, and this just has to boil. It doesn't have to melt. It's already a liquid. This corresponds to the strength of the London dispersion forces of these nonpolar molecules. Let's look at these three molecules. These are all the same size. They actually all have the same chemical formula. These are all isomers of C6H14 with the same chemical formula. And something that is long and spread out is going to have a larger surface area than something that is highly branched and spherical. The smallest surface area you can have for a given volume is the sphere shape. So this is going to be a smallest surface area. This is going to be the larger surface area. And so this is more spread out. It's more polarizable. The electrons can spend more time down on one end than on the other. If you think about this as kind of a stickiness situation, if you have two long flat things that are sticky, like long pieces of tape, it's going to be easier to get them to stick together than if you balled the tape up into a little ball and tried to stick two tape balls together. It's going to be harder. There's not as much contact, not as much surface area to attract to the next molecule over, which is also a sphere. So this long stretched out molecule is going to have the most intermolecular attraction. That's going to give this one the highest boiling point. This one will be in the middle, and this one will be the lowest boiling point. Let's compare these two molecules. We have bromine and we have iodine chloride. And they're similar in mass, they're similar in size and surface area. However, we have the two bromines, which are fairly evenly matched in electronegativity. In fact, they are exactly evenly matched. So this would be a nonpolar molecule. And in contrast, iodine and chlorine, even if you don't remember their electronegativities, remember that electronegativities increase going up and to the right. And on the periodic table, iodine is 2 squares below chlorine. And so it does have a different electronegativity than chlorine. So this would be a polar molecule versus a nonpolar molecule. That would give this a higher boiling point. We have a slightly more negative end and a slightly more positive end, and so these molecules would be able to be attracted to each other with the permanent dipole and not have to rely on London dispersion forces. We have a similar situation here. We have some molecules with polar bonds to the oxygen. Oxygen has a stronger electronegativity than either sulfur or carbon. We have looked at carbon dioxide before and drawn the dipoles with the bonds. So the oxygens are pulling on these electrons that are in these bonds to carbon, and carbon is left electron poor. Both of the oxygens are electron rich. However, overall there is no dipole because these cancel each other out. So we have a nonpolar molecule here. With this molecule, we have oxygens pulling electron density away from sulfur. They're pulling the electrons that are in these bonds. There's some uneven sharing going on. And from left to right, we have some symmetry. Those are canceled out going from left to right, but both of these poles are in the downward direction. And so overall, we have a bit of a dipole facing down. So we have a partly positive end of the molecule here and a partly negative end of the molecule here. Not left and right, but top and bottom, we have some unevenness in the electron distribution. So this would be a polar molecule. And that would give this polar molecule a higher boiling point because, again, we don't have to rely on London dispersion forces. We have this permanent dipole in the molecule. And let's take a look at this last set of molecules. Carbons and hydrogens are generally evenly matched. So areas of molecules that have hydrogen and carbon are considered nonpolar areas of a molecule. So this is important as you get into organic chemistry and you study carbon compounds. That's just something to keep in mind, that things with carbons and hydrogens, areas of a molecule that just have carbon and hydrogen, do not have much polarity. In contrast, carbons and oxygens do have an uneven sharing of the electrons. We have oxygen pulling on electrons away from carbon. Here as well. And then oxygen versus hydrogen is especially unevenly matched. If you remember, we talked about that's a special case in the intermolecular forces. This has an OH group, and so it's capable of hydrogen bonding. Back here with the carbon and oxygen, we have an area of the molecule that has a permanent dipole. This is a polar molecule. We have a little bit of a negative charge on this end of the molecule, a little bit of a positive charge on this end of the molecule. Here we have a negative on this end, positive, I guess, on the other side of where these are pulling toward the oxygen. So this is like superpolar because it has some hydrogen bonding capabilities because of that OH group. This one does not have an OH group. It does still have that dipole. So this has a slight polarity. The polarity of this one is not quite as strong as this one. This one is kind of like, the way it looks, you could even tell that it's kind of clear over here. It just goes straight in this direction, whereas this one has two that are going in similar directions. So you have an overall dipole. So we have a little bit of negativity here, a little bit of positivity here. It's just that it's not as strong in one direction because we do have a little bit of canceling each other out, Whereas this one, we have all the pull is strongly in one direction, and there's nothing pulling in this other direction to cancel it out. So this is sort of a stronger dipole. So I'm going to call this strongly polar. I'm going to call this superpolar because of the hydrogen bonding. And I'm going to call this one just polar. So this hydrogen bonding would have the highest boiling point, and that is what we wanted you to be able to answer in this question. But just to keep you informed, this would have the medium one, and this one would have the lowest boiling point. Just because of the vectors of these dipole moments, these are a little bit less strongly in one particular direction, whereas this one is more strongly in one particular direction.